Hello everyone, welcome to the third hour of current electricity. I hope you enjoyed the last hour. Now, in this hour, we will focus on power and we will focus on solving questions. So, without wasting time, let's start learning the topic of power. So, first of all, what is power? Sir, power is the rate of doing work. Power equals to dW by dt. But here we are talking about charges and current. Now we know that when a charge q is accelerated across a potential drop delta v, then the work done is given by q delta v. Now in current electricity, rather than writing delta v every time, what we write is v. We say that v equals to IR. We do not say delta v equals to IR. But every time we say v here, it means potential drop or the difference in the potential. So we can say from the definition of power, power equals to dw by dt, yes. And in place of the work done, you can write qv. So power can also be written as dqv by dt. Now, if the potential drop is constant, you can take it out of the differentiation. So you can write the same term dqv by dt also as v times dq by dt. And we all know what is dq by dt. dq by dt is the rate of flow of charge, which is current. So if we take the v outside, we get v into dq by dt. And this dq by dt becomes current. So we can say power equals to IV. Now this formula, power equals to current times the potential drop across which the current flows, works for which thing? This thing works for resistance, this thing works for inductor, this thing works for capacitor, this thing works for battery. Which thing? So remember that power equals to IV works on everything. The power dissipated equals to current times the potential drop across which the current is moving. This thing works for all the things. It can be applied on capacitor, inductor, battery, resistor, everywhere. But we know that only for the current flowing through a resistor we can apply Ohm's law. And Ohm's law tells us that V equals to IR. So using Ohm's law, V equals to IR. In the place of I, we can write V by R, or in place of V, we can write IR. So for a resistor, since we know that V equals to IR, for a resistor, we can say that power equals to, in place of I, substitute V by R, or in place of V, substitute IR, and you get power, which is IV, can be written as I square R if you substitute in place of V IR, or can be written as V square by R. So power equals to IV can be used for everything, but power equals to I square R or V square by R should be used only for a resistor. Once more, what is V here? Sir, V is the potential drop across the resistor. V is the potential drop across the resistor. Okay. Now, we can even say if we have got two resistors in series, yes sir. When two resistors are in series, we know that the current flowing through both of them has to be same. Yes. If current flowing through both of them have to be same, to compare the power dissipated by them, I should use IV, I square R or V square by R. So it's better to use I square R when the resistors are in series. Why? Because for resistors in series, the current flowing through them is going to be same. And the power dissipated will be directly in the ratio of their resistance. So if you have got two resistors, R1 and R2 connected in series, then you can say the power dissipated by first resistor equals to I square into resistance of first resistor, and the power dissipated by second resistor equals to I square times resistance of second resistor. If you divided both the side, you can say P1 by P2 equals to R1 by R2, or you can directly say for resistors connected in series, the power dissipated is directly proportional to the resistance. Why? Because the current is same. So the power dissipated is directly proportional to resistance. So you will say if you have got two resistors R1 and R2 in series through which some current I flows. So when connected in series, larger resistance dissipates more power. Obvious. Now similarly, if you have got two resistors R1 and R2 connected in parallel, for two resistors connected in parallel, the potential drop across them have to be same. So you will say for both of them, the potential drop, which is denoted as V, is going to be same. So I can say the power is inversely proportional to the resistance. So out of these two resistors, the one which has got lower resistance will dissipate more power. So remember that in series, bigger resistor dissipates more power as the current is same. When they are connected in parallel, the smaller resistor dissipates more power as the potential drop is same. So you will say when connected in parallel, smaller resistance dissipate more powers. This is something simple which you must know. So I think that you knew already whatever I have taught till now. Now let's talk about something important. In our household, all the appliances are connected in series or parallel. In our household, all the appliances are connected in series or parallel. They are connected in parallel. All the devices in our household work across an AC potential of 220 volt. That's why when I turn off the fan, there is no change in the intensity of light. Okay, so remember that in our household, all the devices are connected in parallel. Now think of a bulb in the house and think of AC. Which one consumes more power? Sir, we all know AC consumes more power. So think over this. In our household, all the appliances are connected in parallel and the AC consumes more power. So the resistance of an AC has to be higher or lower. So sir, as they are connected in parallel, we know that when connected in parallel, the smaller resistance dissipate more power. And we know that our AC consumes more power. Since the AC consumes more power, the resistance of AC has to be smaller compared to that of a bulb. So, in our household, appliances are connected in parallel. Yes, sir. So, AC has less resistance than a small bulb. Keep this small thing in mind. It will help you understand power much better. So, let's see a question. The question goes like, if each resistance in the figure is of 9 ohm, find the reading of the emitter. So here we have got a battery of 9 volt and we can see all the resistances are connected in parallel to this battery. Question is, what will be the reading of this ammeter? So how to solve this question? Whenever you are stuck in any question of current electricity, analyze the potential. So if I assume the potential here to be X, all these points connected by the wire will be at same potential. Okay, and all these points, if you move across the battery, the positive terminal will have a potential of 9 volt higher than the negative terminal. So all these points will have the same potential of X plus 9. Now look at one of the resistor. Across this resistor, there is a potential drop of 9 volt. It has got resistance of 9 ohm. So a current will flow in the direction from higher potential to lower potential in this particular resistor. How much? The potential drop 9 divided by resistance 9. So there will be a current of 1 ampere. So there will be a current of 1 ampere through each and every resistor. Now question is, what will be the reading of ammeter? The reading of ammeter will be because of the combined current flowing in these 5 resistors. In all the 5 resistors, same current of 1 ampere will be flowing. So the reading of this ammeter will be equals to 5 ampere. Definitely here also current of 1111 will be flowing, but this current directly goes back into the battery. So the reading of this ammeter has to be 5 ampere. So main current through the battery I equals to 9 by 1 equals to 9 ampere. So how did you take 9 by 1 equals to 9 ampere? You have got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 resistances of 9 ohm in parallel. So you will say that the R equivalent has to be equals to, using R by N. You have got n identical resistances in parallel, their equivalent combination has to be R by N. So that will be 9 by 9, that will be 1 ohm. So the main current coming out from the battery has to be the potential of the battery, which is 9 volt, divided by the R equivalent of this whole circuit, which is 1 ohm. So you will get a current of 9 ampere. Current through each resistance will be 1 ampere. And only 5 resistances are on the right side of the ammeter, contributes to the passing current through the ammeter. So only these 5 contributes to the current flowing through the ammeter. So the reading of ammeter will be 5 ampere. Simple question. Let's move on and understand more about power. Now what we need to learn about power now is the rating of an electrical appliance. If you go in the shop and buy a bulb, on the bulb something like this is written, X volt Y watt. For example, it is written 220 volt and 60 watt. It means that if you connect this particular appliance across a potential drop of 220 volt, it will consume 60 watt. That's what the rating means. So how do we rate an electrical appliance? So if we have an appliance and the appliance is rated as X volt Y watt, it means that when connected across a potential difference X, the appliance consumes a power Y. When connected across a potential difference X, the appliance consumes a power Y. This is the meaning of rating of an electrical appliance. So if the AC in my house is rated as 220 volt, 1000 watt, it means that when connected across a potential drop of 220 volt, my AC consumes a power of 1000 watt. That's what the whole idea is. Now, using this data, you can find out resistance of the appliance. How? You can say, since we know power equals to V square by R, if a particular appliance is rated as X volt Y watt, it means that the power consumed by the device when connected across a potential drop of X volt is Y watt. So Y has to be equals to the potential drop whole square upon resistance. So the resistance of this particular electrical appliance has to be X square by Y. This will be the resistance of the electrical appliance. So if we know the rating of an appliance, we can find the resistance using R equals to X square by Y. So for example, you have got one appliance in your house which is rated as 100 volt and 50 watt. If the appliance is rated 100 volt 50 watt, what does this mean? When connected across a potential drop of 100 volt, it will consume 50 watt. So now using power equals to V square by R, you can find out the resistance. How? You will say 50, the power consumed, equals to 100 square, the potential drop that has to be applied whole square by R. Now you can see here R equals to 100 square by 50. So that will become 100 into 2, that is 200 ohm. So if you know the rating of an electrical appliance, you can find its resistance. So the resistance comes out to be 200 ohm. Easy? So you need to understand how do we rate an electrical device. Now moving on to another example. An electrical bulb that is made in India is rated 220 volt 100 watt is to be exported to America where the supply line potential is 110 volt. In India, the devices work across a potential drop of 220 volt. In America, the devices work across a potential drop of 110 volt. The question is, an electrical bulb that is made in India rated at 220 volt 100 watt is to be exported to America where the supply line potential is 110 volt. How will you re-rate it to export it? So in India, you have given rating as 220 volt 100 watt. Okay. But the person using in America will use it across a potential drop of 110 volt. So what will be the power consumed by the same bulb in America? That's what the whole question is. So you will say resistance of the bulb is not being changed. Only the bulb is being re-rated. We are not at all opening the bulb. We are not changing its circuitry or the coil or filament anything. We are just re-rating it. So you will say, since we know that power equals to V square by R, one can say when the bulb is being used in India, we know that the power consumed is 100. And let's say the bulb has got a resistance R. So you will say 100, the power consumed in India, equals to the potential drop that is needed to be applied whole square divided by R. So now you know what is the resistance of the bulb. We are just re-rating the bulb. We are not at all changing its resistance. So let's say for the supply of 110 volt, wattage is X. It means that when connected across a potential drop of 110 volt, it consumes a power X. So for the same bulb, you will say the power consumed X has to be equals to the potential drop of 110 volt applied whole square upon the resistance. Now from these two equations, you can easily find out what will be the power rating of the same bulb when it is used in America. So dividing both the sides, on the left hand side you will get 100 by X and on the right hand side you will get 220 whole square by R upon 110 whole square by R. So the R and R get cancelled. What you get is 220 square by 110 square, that gives you 4. So once you know this is 4, so if 100 by X equals to 4, this means that X has to be 25 watt. if X is 25 watt, then the same bulb will consume a power of 25 watt in America. So the rating has to be 110 volt and 25 watt. Now, bachcho, important thing here. You do not need to solve this much. You could have directly said, sir, power equals to V square by R. Yeah, you are not at all changing the resistance of the bulb. Yes, you are just changing the potential drop across which it is being used. Yes. So if the potential drop across which it is being used becomes half, power equals to V square by R. If the potential drop becomes half, the power dissipated becomes 1/4. So it has to be 1/4 of 100. It has to be 25 watt. So the answer has to be 110 volt and 25 watt. If I would have said here, it is being sent to a country where the supply line potential is 440 volt, then what will be the answer? Simple. You will say, sir, if the supply line potential becomes double, then the power dissipated becomes 4 times. So then we will re-rate this same bulb as 440 volt and 400 watt. So these type of simple questions can be asked. Now the next question. If two bulbs of rating 220 volt 100 watt and 220 volt 50 watt are connected in series, 220 volt 100 watt and 220 volt 50 watt are connected in series, then which one of them will glow brighter? Let's see the next example. If two bulbs of rating 220 volt 100 watt and 220 volt 50 watt are connected in series, which one will glow brighter? Now the common sense says that the bulb of 100 watt glows brighter than the bulb of 50 watt. But do understand, whenever any company designs a bulb, they are designed to be used in the household. And when we mean to use any device in the household, they are meant to be used in parallel. Now some idiot connected them in series the way they shouldn't be used. And as a matter of fact, the answer comes out to be reverse. The 50 watt bulb glow brighter when connected in series compared to 100 watt bulb. Why? Let's see. So the appliances are meant to be used in parallel. That's how the company designed it. If connected in parallel, 100 watt bulb will glow more. That's for sure because it has got more power rating. Now you will say, also we know that power equals to V square by R. These devices are meant to be operated in parallel. They are meant to be operated across the same potential drop of 220 volt. But some idiot connected them in series. Now you can say that as power equals to V square by R, the device which has got higher power rating will have a lower resistance. So from here I can say that the resistance of 100 watt bulb has to be less than the resistance of 50 watt bulb. Remember I told you the example in my household, which one has got higher resistance, the AC or the bulb? Both of them are meant to be used in parallel. Who dissipates more power? Sir, AC. So if the AC dissipates more power, it has got lesser resistance. And since the bulb dissipates less power, it has got more resistance. That's why the appliance which has got lower wattage rating has got more resistance. So here, since the bulb of 50 watt has got lower power, it has got higher resistance. So you can say resistance of 50 watt bulb is more than the resistance of 100 watt bulb. Now they are not at all meant to be used in series. But if connected in series, the bulb of higher resistance will dissipate more power. Why? Because once they are connected in series, we know that the current flowing through both of them will be same. And if the current flowing through both of them is going to be same, then the higher resistance will dissipate more power. Hence, the bulb of resistance 50 ohm will dissipate more power than the bulb of resistance 100 ohm. So the bulb of 50 ohm rating will glow more if connected in series. Okay. So now we will talk about something called the maximum power transfer theorem. The name itself is important. Students remember the result, but they do not remember the name of the theorem. Why? Because in the name of the theorem lies a deep concept. The name is maximum power, and this word is important, transfer theorem. What is the maximum possible power that can be transferred by a cell to a load resistance? Let's say we have got a real world cell, and every real world cell has got some internal resistance. And we have connected this cell to one more resistance, say R. And we are variating this particular load resistance. The arrow symbol tells us that this load resistance's value can be variated. So, for which value of load resistance the power dissipated by the load resistance will be maximum, or the power transferred to the load resistance will be maximum, that's what we get from the maximum power transfer theorem. So the theorem says that the power delivered by the cell to the load resistance will be maximum when the load resistance will be equal to internal resistance of the cell. Once more, the power delivered by the cell to the load resistance will be maximum when the load resistance will be equal to internal resistance of the cell. I am nowhere saying that the power delivered by the cell will be maximum when the load resistance equals to internal resistance of the cell. Nobody ever said that. What I am saying here is the power dissipated by the load resistance will be maximum when the load resistance equals to internal resistance of the cell. Keep this in mind. Now, question is, what will be the magnitude of this maximum possible power dissipated by the load resistance? So you will say, the theorem tells me that the power dissipated by the load resistance will be maximum when the load resistance will be equal to internal resistance. When the load resistance will be equal to internal resistance, the current driving in the circuit has to be equals to E by 2R. And using this current in the circuit, I can find out the maximum possible power dissipated by the load resistance. So you can say the maximum power dissipated has to be equals to the current flowing through the load resistor when its resistance is equal to internal resistance of the cell whole square into R. I have used power dissipated equals to I square R. So the maximum possible power that can be dissipated by the load resistance has to be equal to E square by 4R. Okay, just solve it out. So remember that the power dissipated by load resistance is maximum when it is equal to internal resistance of the cell. And the value of this maximum possible power dissipated by the load resistance equals to EMF whole square upon 4 times the internal resistance of the cell. If we plot the graph of power dissipated by the load resistance versus the load resistance, the graph looks something like this. There is a particular value of load resistance for which the power dissipated by the load resistance is maximum, and the theorem has already told us that the power dissipated by the load resistance will be maximum when the load resistance will be equal to internal resistance of the cell. So here P represents the power dissipated by the load resistance, not at all the power dissipated by the cell, the power dissipated by the load resistance. Now, if for two value of load resistances, let's say R1 and R2, the power dissipated is same. Let's say there are two value of load resistance R1 and R2 for which the power dissipated comes out to be same. Then how can we write the internal resistance of the cell in terms of R1 and R2? So this is a result you need to remember. It will be helpful for your examination. So if for two value of load resistance R1 and R2, the power dissipated is same. Let's say for two values of load resistance R1 and R2, the power dissipated comes out to be same. Then the internal resistance of the cell has to be geometric mean of R1 and R2. Geometric mean of two number A and B is root AB. Arithmetic mean of two number A and B is A plus B by 2. So beta, remember that if for two value of load resistance we get the same power dissipated, then the internal resistance of the cell has to be geometric mean of those two resistances R1 and R2. So remember that R equals to root R1 R2. This is a result that will help you solve question faster in your NEET examination. Let's move on to a simple question. Determine the maximum power that can be delivered by a cell of EMF 6 volt and internal resistance 1 ohm to a load resistance. Determine the maximum power that can be delivered by a cell of EMF 6 volt and internal resistance 1 ohm to a load resistance. We have just learned that the power dissipated maximum equals to the EMF of the cell whole square divided by 4 times the internal resistance. So I will simply get 6 square by 4 times 1, that becomes 36 by 4, that is 9 watt. Or you can go from the basic. For maximum power transfer, the load resistance should be equal to internal resistance, and which is given as 1 ohm. So visualize a circuit in which the load resistance is same as the internal resistance of the cell. If you have got this circuit, what will be the current flowing in this circuit? So you will say that the current flowing in this circuit has to be equals to 6 upon resistance of circuit 1 plus 1 2. So the current flowing has to be 3 ampere. Once you know the current flowing through the load resistance when it dissipates maximum power is 3 ampere, then the power dissipated has to be I square R. So the power dissipated equals to I square R equals to 3 square the current flowing through it when it dissipates maximum power multiplied by its resistance. So that gives you 9 watt. Okay, let's move on. A current of 2 ampere flows in the system of conductor as shown. The potential difference VA minus VB will be. Now this is an important question. Why? Because it sets the foundation for Wheatstone Bridge. So the question is, here you can see you have got 2 ohm, 3 ohm, 3 ohm, 2 ohm. There are 4 resistors. Now question is, what is the value of VA minus VB? So how to find it? So tell me, when the current reaches this point, it has got 2 options, to go in the upper line or to go in the lower line. Yesterday we have learned that if we have got 2 resistances R1 and R2 in parallel, then the current going through R1 is R2I by R1 plus R2, and the current going through R2 is R1I by R1 plus R2, right? Now since the whole upper line has got resistance of 5 ohm, 2 ohm plus 3 ohm in series, and the lower line also have got resistance of 5 ohm, 3 ohm plus 2 ohm in series, since both the line have got same resistance, equal amount of current will go in both of them. So in the upper line, the current going will be 1 ampere. In the lower line, the current going will be 1 ampere. Our mission is to find VA minus VB. How to do? Let's see. So in the given circuit, 2 ampere current divides equally at the junction D along the path DAC and DBC. Why equally? Because sir, the upper line and lower line have the same resistance of 5 ohm, 5 ohm. That's why the current divide equally. Each path carries 1 ampere of current. So the current flowing through upper line will be 1 ampere, as well as the current flowing through lower line will also be 1 ampere. Our mission is to find VA minus VB. Okay. Now you will say, when the current of 1 ampere flows through this 2 ohm, there will be a potential drop, right? How much? Sir, I 1 ampere into R 2 ohm. So there will be a potential drop of 2 volt across this 2 ohm. Similarly, there will be a potential drop of 1 into 3 I into R across this 3 ohm. So you will say that potential difference between D and A, will be equals to VD minus VA. And since a current of 1 ampere flows here, VD minus VA has to be equals to IR, that will be 2 volt. So think of it as your first equation. Similarly, potential difference between D and B, has to be equals to VD minus VB. And in this line also current is 1 ampere. So you will say VD minus VB, the potential difference across this 3 ohm resistor has to be equals to 1 into 3, that will be 3 volt. Our mission is to find what? Our mission is to find VA minus VB. We know what is VD minus VA. So VD minus VA is 2 volt. We know what is VD minus VB. Okay, that is 3 volt. Our mission is to find VA minus VB. What to do? So beta, simply do equation 2 minus equation 1. When you do equation 2 minus equation 1, on the left hand side, VD will get cancelled and you will get minus VB minus VA, so that becomes VA minus VB. And on the right hand side, you will get 3 minus 2, that will be 1 volt. So on solving 1 and 2, we get VA minus VB equals to 1 volt. It means that the potential of A is higher than that of B by 1 volt. Even without raising pen, I could have said that VA minus VB is going to be positive. Sir, why? Think of it this way. The net potential drop in both the parallel lines have to be same. The net potential drop across this 2 ohm and 3 ohm combination and across this 3 ohm and 2 ohm combination has to be same. Yes, sir. Now, in the upper line, since 2 and 3 are in series, more potential drop will take place across 3 and less potential drop will take place across 2. And while in the lower line, more potential drop will take place across 3 and less potential drop across 2. So going from D to A, we find less potential drop. Going from D to B, we find more potential drop. So going from here to here, less potential drop. Going from here to here, more potential drop. So that's why the final potential of A has to be more than the potential of B. That's why I already knew before solving VA has to be greater than VB. So VA minus VB has to be something positive. Think over it. So moving on to the Wheatstone bridge. What is a Wheatstone bridge? A combination of 5 resistors connected like this. That's called Wheatstone bridge. Now we will say that no current will flow through R5. No current will flow through R5 if the potential of X becomes equals to potential of Y. So if potential of X equals to potential of Y, then no current flows through the fifth resistance. And if no current flows through fifth resistance, we can think it as if it is not at all part of system. So we will have just these 4 resistors. Those will be R1, R2, R3 and R4. Now here you will say that R1 and R2 are in series, R3 and R4 are in series, and the combination of R1 and R2 is in parallel with the combination of R3 and R4, and you can find out the equivalent resistance easily. But what is the condition for potential of X to be equal to potential of Y? So forget R5 for once. Think of the other 4 resistances and think of the point X and Y. Now you will say if a potential drop delta V is applied across this combination, in upper line you have got R1, R2, in lower line you have got R3, R4, and if a potential drop delta V is applied across this particular combination, then the current flowing in the upper line has to be equals to the potential drop across it. Now the upper line has got resistance of R1 plus R2 and the potential drop across it is delta V. So the current flowing through the upper line will be delta V upon R1 plus R2, potential drop across it upon its resistance. Similarly, the current flowing through the lower line, if it is applied across a potential drop delta V, will be the potential drop upon the resistance of the lower line, which is R3 plus R4. Now we know the current in the upper line, current in the lower line. Our mission is to find the condition for potential at X to be equal to potential at Y. If you want the potential at X to be same as the potential at Y, the basic argument is whatever potential drop takes place across R1 going from A to X, the same potential drop should take place across R3 going from A to Y, so that the potential of X and Y comes out to be equal. So you can say Vx, the potential at X, has to be equal to potential at A minus the potential drop going from A to X, and the potential drop will be equals to resistance R1 times the current, which is delta V upon R1 plus R2. Similarly, the potential at Y can be written as potential at A minus the potential drop in going from A to Y, which will be nothing but the resistance R3 times the current flowing through it, which is delta V upon R3 plus R4. Now if you want potential at X to be equal to potential at Y, you should equate the two right hand sides. The VA get cancelled, the minus get cancelled. So for Vx to be equals to Vy, what we get is R1 delta V upon R1 plus R2 has to be equals to R3 delta V upon R3 plus R4. Now if you flip it both the sides, what you get is R1 plus R2 upon R1 delta V equals to R3 plus R4 upon R3 delta V. Now bachcho cancel out delta V, yes. Now you have got R1 plus R2 by R1, that can be written as 1 plus R2 by R1. And on the right hand side you have got R3 plus R4 by R3, that is 1 plus R4 by R3. So cancelling out 1 on both the side, what you get is R2 by R1 equals to R4 by R3. R2 by R1 equals to R4 by R3, or cross multiply, you will get that R1 R4 equals to R2 R3. So on flipping and cancelling out delta V, you get this, and that can be written as R2 by R1 equals to R4 by R3, or the condition R2 into R3 equals to R1 into R4. R2 into R3 equals to R1 into R4. R2 into R3, the diagonal ones, equals to R1 into R4. People also like to write the same thing as R1 by R3 equals to R2 by R4. You can write the same thing this way as well. Now, this is the condition for Vx to be equals to Vy. Sometimes in question, they might ask, what is the condition between R1, R2, R3, R4 for the potential at X to be greater than the potential at Y? So if you want potential at X to be greater than the potential at Y, just place here a greater than sign. So when you place the greater than sign, you get potential at x to be greater than potential at y. The condition is R2 R3 R2 into R3 should be greater than R1 R4. If you want the potential at x to be greater than potential at y, then R2 R3 should be greater than R1 R4. And if you want potential at x to be less than the potential at y, change the sign here, change the sign here, you'll get R2 R3 must be less than R1 R4. This is the condition. So now we will talk about something called extended Wheatstone bridge. If I give you this type of question, that you have got these 5 resistors. Okay, so the resistors are 2 ohm, 4 ohm, 6 ohm, 12 ohm, and there is one more resistor of 7 ohm. And I ask you, determine the R equivalent of this circuit between point A and B. How will you find? So you will say, sir, since 2 by 4 half equals to 6 by 12 half, so this is a balanced Wheatstone bridge. And since it is a balanced Wheatstone bridge, no current will flow through this fifth resistance of 7 ohm. So you can throw it out of the circuit. Now the resistance of upper line will be 2 plus 6, which is 8. The resistance of lower line will be 4 plus 12, which is 16. Now you have got two resistors of 8 ohm and 16 ohm in parallel. You can find their R equivalent, right? But what if rather than giving you 5 resistors, I give you more? Let's say I give you this type of circuit. But here also the resistors are in specific ratio. Let's say 2 ohm, 6 ohm, 3 ohm, 9 ohm, 4 ohm, 12 ohm, 16 ohm, 48 ohm, and let's say here we have got 5 ohm, 7 ohm, 11 ohm. And now I ask you, determine the equivalent resistance between point A and B. So you will say, sir, you have just multiplied more and more number of Wheatstone bridges. So this is kind of extended Wheatstone bridge. Now here the resistances are in a specific ratio, 1 is to 3, 1 is to 3, 1 is to 3, 1 is to 3. So no current will flow through these 3 resistors. Hence the overall resistance of the upper line can be taken as 2 plus 3 plus 4 plus 16, and the overall resistance of lower line can be taken as 6 plus 9 plus 12 plus 48, and then you can find the parallel combination. So keep this thing in mind when I teach you extended Wheatstone bridge. So you will say, for a balanced Wheatstone bridge, for potential at x to be equal to potential at y, the condition is that R1 by R3 should be equal to R2 by R4. Similarly, if you see this type of circuit, for the potential of W to be same as X and for the potential of Y to be same as Z, so that you can remove the resistances connected between them. For the potential of W to be same as X and for the potential of Y to be same as Z, you will say that the condition is R1 by R4 should be equal to R2 by R5 should be equal to R3 by R6. So this is the condition for removing the resistors placed in the case of extended Wheatstone bridge. So let's do some question based on Wheatstone bridge. The first question goes like, in the given figure, equivalent resistance between A and B will be. So first of all, you need to check this is a balanced Wheatstone bridge or not. So 3 into 8, 24, 6 into 4, 24. Since R1, R4 equals to R2, R3, that's why the potential of these 2 points will be same. As the potential of these 2 points will be same, no current will flow through the 7 ohm. As no current will flow through the 7 ohm, throw it out of the circuit. Once you throw it out, now the upper line will have resistance of 7 ohm, the lower line will have resistance of 14 ohm. So the same thing is written here. The upper line will have resistance of 7 ohm, the lower line will have resistance of 14 ohm. So the equivalent resistance when you solve it comes out to be 14 by 3 ohm. How? 7 into 14 upon 7 plus 14. So that becomes 7 into 14 upon 21. Cancel out, here you get a 3. So the answer comes out to be 14 by 3 ohm. Easy. Let's see the next one. In the combination of resistances shown in the figure, the potential difference between B and D is 0 when the unknown resistance X is. The question is, what is the value of X so that the potential difference between point B and D is 0? It means that the point B and D are at same potential. So you will say, sir, it has to be a balanced Wheatstone bridge. Now see, the resistance between A and B is 12 ohm and 4 ohm connected in series. So rather than thinking of 12 and 4, think of a single resistance of 16 ohm. Now here you have got two resistances of 1 ohm and 1 ohm connected in parallel. So rather than thinking of 1 ohm and 1 ohm, think of only a single resistance of half ohm. So here 16, there half. Similarly, here you have got 1 and 3. Rather than thinking of 1 and 3 between A and D, think of a single resistor of 4 ohm, and here you have got X. If the potential of B and D is same, it means that R1, R4 has to be equals to R2, R3. So you will say 16 into half. The diagonal relationship 16 into half has to be same as 4 into X. Game over. So you will say 8 equals to 4X, hence X has to be equals to 2. Okay. So the same thing is written here. The potential difference across B and D will be 0 when the circuit will act as a balanced Wheatstone bridge. And for this Wheatstone bridge to be balanced, P by Q has to be same as R by S. So 16 by X has to be same as 4 upon half. And on solving this, you get X equals to 2. Not at all rocket science. Okay, focus on concept. So now the next example. A torch bulb is rated at 4.5 watt and 1.5 volt. Is connected as shown in the figure. Where is the figure? Here is the figure. So the EMF of the cell needed to make the bulb glow at full intensity. So you know that this bulb works properly when it is connected across a potential drop of 1.5 volt. So you want that the potential drop across the bulb has to be 1.5 volt. And we can see that this bulb, a resistance of 1 ohm and the battery are connected in parallel. So when the potential drop across the bulb will be 1.5 volt, even the potential drop across this resistor will be 1.5 volt, and the potential drop across the cell will also be 1.5 volt. Now, if you want this bulb to work properly and it is rated at 4.5 watt, 1.5 volt, what is the meaning of this? This means that when connected across a potential drop of 1.5 volt, it will consume a power of 4.5 watt. So can you tell me how much current has to be flowing through the bulb at its rated voltage? So you will say, sir, the first formula we learned for power is power equals to IV. Yeah, later for resistor, we even got power equals to I square R, or we even got power equals to V square by R. But power equals to IV is the basic. Now here the power consumed is 4.5 when a potential drop of 1.5 is applied. It means that when you connect it across a potential drop of 1.5 volt, then the current in the circuit is 3 ampere. So if the potential drop across the bulb is 1.5 volt, then the current flowing through the bulb has to be 3 ampere. If the same potential drop is there across this resistor of 1 ohm, then you will say that the current in the resistor has to be 1.5 divided by 1, that is 1.5 ampere. The current going through the bulb is 3, the current going through the 1 ohm resistor is 1.5. So what must be the current coming out of the battery? So the current coming out of the battery must be 4.5 ampere, 3 plus 1.5. Now you know that the potential drop across a discharging cell is given by EMF minus IR. Here you know that the potential drop has to be 1.5. EMF is asked from us. Current that has to flow from the battery is 4.5, and the internal resistance is given as a bad number 2.67. So from here you get that the EMF of the cell has to be 1.5 plus 4.5 into 2.67. That's how you get the answer. So let's look at the solution once more. When the bulb glows with full intensity, the potential difference across the bulb is 1.5 volt, yes. So the current through the bulb and resistance of 1 ohm are 3 ampere and 1.5 ampere. So when you have got this bulb and it glows at its full intensity, from P equals to IV, you can find that the current flowing through the bulb must be 3 ampere. And for a potential drop of 1.5 volt across the resistor, the current flowing through it must be 1.5 ampere. So the main current from the cell has to be 3 plus 1.5, that is 4.5 ampere. By using delta V equals to E minus IR or EMF equals to delta V plus IR, we can get the answer. So using EMF equals to delta V plus IR for a discharging cell, substituting delta V as 1.5 and current as 4.5 and internal resistance as 2.67, we get that the EMF has to be equals to 1.5 plus 4.5 into 2.67, which approximately comes out to be 13.5 volt. Okay, let's see the next example. A wire has resistance of 12 ohm. A wire has resistance of 12 ohm. It is bent in the form of a circle. It is bent in the form of a circle. The effective resistance between 2 points on any diameter is equal to. So what is the effective resistance between 2 points on any diameter. So you will say if the current enters from here and exits from here, the whole loop has got resistance of 12 ohm. We know that resistance equals to rho L by A. So the resistance is directly proportional to length. For the whole loop, for the whole length, the resistance is 12 ohm. So for the half length, the resistance has to be 6 ohm. So this will have 6 ohm, this will have 6 ohm. Now these two 6 ohms are in parallel. So you will say that the R equivalent has to be equals to 6 by 2, that will be 3 ohm. Okay. So equivalent resistance of the following circuit will be, rethink of the circuit. The whole ring has got resistance of 12 ohm. So the upper half will have 6 ohm, the lower half will have 6 ohm, and these two 6 ohm resistors are in parallel. So the R equivalent has to be nothing but 3 ohm. Now beta, if in the same question they give you question like this, for this whole wire resistance is 12 ohm, determine the effective resistance between two points A and B as shown in the figure, such that the radius vectors from A and B are at angle of 90 degree. What will be your answer? So you will say, sir, if the whole wire have got 12 ohm, then 1/4 length will have 1/4 the resistance. So this part will have 3 ohm, and the other part, which is 3/4 of the whole length, will have 3/4 of the overall resistance of 12, that will be 9 ohm. So this will have 9 ohm. So the effective resistance has to be the parallel combination of 3 and 9, and the parallel combination of 3 and 9 gives you 3 into 9 by 3 plus 9, which is 12. So here you get a 4, so that comes out to be 9 by 4, which is 2.25 ohm. So this is how these type of questions are asked. Now let's do this question but for a general angle alpha. So question is, a wire of resistance R is bent into circular ring of radius R, equivalent resistance between 2 points X and Y on it circumference, when angle XOY is alpha is given by. So the whole ring has got resistance R. You have turned it into forming a circle. There are 2 points on this circle, let's say X and Y, and XOY, X center and Y form an angle alpha. So you need to tell what is the effective resistance between X and Y. And this is easy. This is actually easy. You will say if the whole circle has got resistance R, then this part of circle will have resistance R into alpha by 2 pi from direct proportionality. As you know, for the whole circle subtend at center the angle 2 pi. For the whole circle, resistance is R. So for an arc subtending angle alpha, the resistance has to be R into alpha by 2 pi. Similarly, the remaining part of the circle subtend an angle 2 pi minus alpha at the center. So its resistance will be R into 2 pi minus alpha upon 2 pi. So you will say the effective resistance between X and Y has to be the parallel combination of R alpha by 2 pi and R into 2 pi minus alpha by 2 pi. So you will get R equivalent to be equals to R alpha by 2 pi into R into 2 pi minus alpha by 2 pi divided by resistance of the whole ring, R1 plus R2, which is nothing but R. So cancel out R, you get R into alpha into 2 pi minus alpha upon 4 pi square. Let's do it once more slowly. So visualize the ring. Think of the point X and Y. The angle subtended is alpha. Think of resistance of this part as W and this whole part's resistance as Z. So you will say resistance of XWY, this part will be equals to R upon 2 pi R into R alpha. So that gives you R alpha by 2 pi, which I have already said. Similarly, the resistance of XZY part will be equals to R upon 2 pi R, resistance upon overall circumference multiplied by R into 2 pi minus alpha. This is R1. So that gives you R upon 2 pi into 2 pi minus alpha. Once you know resistance of both the parts, resistance of this part is R alpha by 2 pi, resistance of the remaining part is R into 2 pi minus alpha by 2 pi, game over. Now you have to just do R1 into R2 upon R1 plus R2. And you know that R1 plus R2 is nothing but R. So you will say R equivalent equals to their multiplication upon their sum. So simply multiply them upon their sum. This denominator part will be nothing but R. So what you get here, if you substitute an R get cancelled. So you get R alpha into 2 pi minus alpha upon 4 pi square. R alpha into 2 pi minus alpha upon 4 pi square. Revise this question once, it won't take more than 10 seconds. So just visualize the question and the answer. Let's move on. Three resistances, each of 4 ohm, are connected in the form of an equilateral triangle. The effective resistance between the two corners is. So here you have got three identical resistances of 4 ohm each along the three sides of an equilateral triangle. You need to find the equivalent resistance between any two corners. So you will say the resistance of this part will be 8 ohm, and here you have got 4 ohm. So the 8 ohm is in parallel with 4 ohm. So the R equivalent will be equals to 8 into 4 upon 8 plus 4, that becomes 32 by 12 ohm. You can cancel by 4, so you get 8 by 3 ohm. That's all. So visualize the figure. You will say these two are in series. So their equivalent resistance is 8 ohm, and this 8 ohm is in parallel with 4 ohm. So the R equivalent comes out to be nothing but 8 into 4 upon 8 plus 4, that comes out to be 8 by 3 ohm. Simple question. Let's move on. Find the equivalent resistance between point A and B. So here we need to find the equivalent resistance between point A and B. This question is simply based on reducing the circuit. So here you will say these two are in series. Since these two are in series, replacing both of them, I can visualize a single resistor of 2R. And then this 2R and this 2R are in parallel. So 2R parallel 2R gives you R. So removing whole of this part, you can place a single resistor of R. So once we have done that, removing this whole part, we have placed a single resistor of R. Now we can see that this R and this R are in series. Okay, and this whole combination of 2R is in parallel with this 2R. So now I can remove this much part and place a single resistor of R. 2R parallel 2R gives you R. Once you do that, you find that now this resistance is R. In series you have got one more R. So this whole combination is of 2R, and this 2R is in parallel with 2R. So again remove whole of this part and place a single resistance of R, and this became your previous question. So now you have got R series R and one more R in parallel. So you will get 2R into R upon 2R plus R, which is 3R. So cancelling out 1R and 1R, the answer comes out to be nothing but 2R by 3. Let's see the next example. Now here is a question based on symmetric circuits. What I want you to understand here, let's say the terminal A is connected to a battery of higher potential and a terminal A dash connected to lower potential. So current will enter from A and it will exit from A dash. The current entering the loop has to be same as the current exiting the loop, right? Now bachcho, do understand, as the current keep on moving forward in the resistors, the potential should decrease. Since this particular circuit has a symmetry, as the current keep on moving forward, the potential keeps on decreasing. The point 6 and point 5 will be at same potential. The point 2, the point O, the point 4 will be at same potential. And as the current keeps on moving forward, the potential keeps on decreasing, and the point 7 and the point 8 will be at same potential. What did I do in the question where I have got 2 points connected to earth? I said that since they are at same potential, you can assume them to be joined by a wire, or you can simply assume these two grounded points to be joined. The same concept I am going to use here. I will say that since 6 and 5 are at same potential, you can assume them to be joined. Since 7 and 8 are at same potential, you can assume them to be joined. Since 2 and 4 are at same potential, you can assume them to be joined, and this is called folding the circuit. So if I visualize the same circuit after folding, the point 2 and 4 brought to same place, the point 5 and 6 brought to same place, they have been joined. The point 7 and 8 brought to same place. Now you have got two resistors placed between 1 and 6 because 6 is same as 5. So 1 and 5, one connection, 1 and 6, one connection. Here you can see between 1 and 5, one connection, 1 and 6, one connection. So I have folded the circuit. Once this circuit has been folded, solving it becomes really easy. In place of these two, you can place a single resistance of R by 2. In place of these two, you can place R by 2. In place of these two, you can place R by 2. In place of these two, R by 2, R by 2, R by 2. So once you do that, you get this type of circuit. Now you have got R by 2, 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 R by 2. These two R by 2s in series become R. These two R by 2 in series becomes R. And R parallel R, R parallel R again give you R by 2. So now you have got R by 2 in series with the whole combination of this, which is R by 2 in series with R by 2. So you get R by 2, R by 2, R by 2. So the equivalent resistance comes out to be nothing but 3R by 2. Okay. Let's see the next example. 5 resistances are combined according to the figure. Where is the figure? Okay, here is the figure. The equivalent resistance between point X and Y will be. So here we have got 5 resistors, 10 ohm, 10 ohm, 20 ohm, 10 ohm, 10 ohm. What is the equivalent resistance between the point X and Y? So I know that many of you know this standard problem. This is nothing but a Wheatstone bridge drawn in a different fashion. So you will say the equivalent circuit of above can be redrawn as this. This is the same circuit. Name this point as A and this point as B and rearrange the circuit little bit. So move the A up and B down, and on rearrangement it looks something like this. Now you can see this is a balanced Wheatstone bridge. Since it is a balanced Wheatstone bridge, this into this equals to this into this, 100. So I can remove this 20 ohm, and once I remove the 20 ohm, game over. You will say that the resistance of upper line is 10 plus 10, 20. The resistance of lower line is 10 plus 10, 20. You have got 20 parallel 20. So the R equivalent has to be equal to 10 ohm. So we will say this is a balanced Wheatstone bridge. So the current through AB is 0. So R equivalent comes out to be equals to 1 by 20 plus 1 by 20. 1 upon R equivalent equals to 1 by 20 plus 1 by 20. So you get that is equals to 1 by 10. So R comes out to be nothing but 10 ohm. Easy question. Let's see the next one. What will be the equivalent resistance of the circuit shown in the figure between point A and D? So here you have got this circuit. You need to tell what is the equivalent resistance between point A and D. So think that as if you have got a battery connected between point A and D. So the current will enter from A, it will go here, it will split into two parts. Now on reaching here, will some current go towards C? No. Why? Because it will go here and then where? Where it will go ahead. It is not at all connected to anything. That's why any current entering from A, not any part of that current will go towards C. By the same logic, not any part of the current coming from here will go towards B. So these two resistors are drawn just for time pass. Now once you forget these two resistors, the solving of circuit is quite easy. You just have this circuit. Forget about them. Do not even think about them. Do not even draw them. So now this is your circuit and you have got resistor of 10, 10, 10, 10, 10, 10. Now you will say these two 10s are in series 20. These two 10s are in series 20. 20 parallel 20 combined gives you 10. So you have got 10, 10, 10. So R equivalent has to be 30 ohm. So the equivalent circuit of the above figure between A and D can be redrawn only as this much part. I have just thrown out this C part and this B part because no current will go into them. Sir, why no current will go? Beta, if current will go, where will it go? It will enter, then where? It will jump in the air. No, no. So that's why no current will go in these two arms. That's why I have thrown them out of the circuit. And once you have thrown it out, you will say for this much part, the resistance has to be 20 parallel 20, which is 10. So you get 10 series 10 series 10. So R equivalent comes out to be nothing but 30 ohm. Simple question. So now next example. In the network shown in figure, each resistance is equal to 2 ohm. Where is the network here? The resistance between A and B is. So what is the equivalent resistance between point A and B? And this question is simple question. All you need to do is you just have to unfold the circuit, move A and B outside. If you move A and B outside, move the point A here. So you will say the circuit on redrawing will look something like this. So this is point A and I have moved the point B also outside. This is now the point O, and forget this part of circuit and this part. Now what does the remaining circuit looks like? So you will say, sir, the remaining part of circuit looks like a balanced Wheatstone bridge. 1, 2, 3, 4, 5. And a balanced Wheatstone bridge between the point A and E. So think after unfolding it, taking the portion COD in the figure outside to the left, the above circuit will now act as each resistance is of 2 ohm. The circuit will behave as a balanced Wheatstone bridge and no current will flow through which line? Through the line CD. Through the line CD. So now what will be the equivalent resistance? So sir, through this part out of the circuit, as no current will flow through it. So you get 2 ohm, 2 ohm, 2 ohm, 2 ohm. So you have got 4 ohm in parallel with 4 ohm, and 4 ohm parallel 4 ohm gives you nothing but 2 ohm. So the R equivalent comes out to be 2 ohm between point A and B. Moving on, 7 resistances are connected as shown in figure. Where is the figure here? The equivalent resistance between point A and B is. Now these type of questions are not tough. If in a question you don't know the potential of any point, assume some potential and start rethinking. So you will say, okay, I know that all these points are at potential A, right? Similarly, all these points are at potential B. I don't know what is the potential of all these points. Let's call them C. And I don't know what is the potential of all these points. Let's call it D. So you will say this 6 ohm is connected between B and D. This another 6 ohm is also connected between B and D. And you can see these two 10 ohms are connected between A and C. So try to redraw the circuit. Think of point A, C, B and D. Here you can see between A and C, we have got two resistors of 10 ohm in parallel. So rather than drawing two resistors of 10 ohm in parallel, I am drawing a single resistance of 5 ohm. So these two drawn. Here you have one more resistor of 5 ohm between A and D. 5 ohm between A and D. Here you have got a resistance of 3 ohm between C and B. Resistance of 3 ohm between C and B. Cancel out this one, drawn. This one drawn. One resistor of 8 ohm between C and D. One resistor of 8 ohm between C and D. And two resistors of 6 ohm between B and D. Two resistors of 6 ohm in parallel between B and D. Rather than drawing two, draw only one of 3 ohm between B and D. So here you can see again a balanced Wheatstone bridge. So there is no current through this central line. The resistance of upper line is 5 plus 3, 8. Lower line is 5 plus 3, 8. 8 parallel 8 gives you R equivalent of 4. So the answer to this question is 4. So when you try to solve it, you can see these two 10 and 10 are in parallel. Throw them out, place a single one of 5 ohm. Similarly, these two 6 and 6 are in parallel. Throw both of them out and place a single one of 3 ohm. And when you redraw it, you get this type of circuit. Now your mission is to find equivalent resistance between A and B. So you can see that there is a balanced Wheatstone bridge 5, 5, 3, 3. Okay, so once you can see this balanced Wheatstone bridge, you can say that no current flows through this 8 ohm. So in the upper line, resistance is 5 plus 3, 8. In lower line, 5 plus 3, 8. So you get the R equivalent of this circuit is nothing but 5 plus 3 parallel 5 plus 3. That comes out to be 8 parallel 8. That is 4 ohm. Okay, next example. The equivalent resistance between point A and B in the circuit shown will be. So here you have the circuit. What is the equivalent resistance between point A and B? How to solve? Now see kids here. I just told you a case of symmetry, right? Now I can say that if let's say we have connected a battery between A and B, okay, the current will enter from A and it will exit from B. The current entering the loop has to be same as the current exiting the loop. As the current keep on moving forward and forward through the resistances, the potential keeps on decreasing. Now, here you can draw a line, vertical line, and you can say all the points on this line of symmetry will be at same potential. So how to solve this particular question? You will say that there is a resistance R, there is a resistance R, there is a resistance R, there is one more resistance R, there is one more resistance R, and there is one more resistance R. But I have left out one resistance purposefully, this one. Now rather than thinking of this single resistance as R, think of two identical resistances R by 2, R by 2, so as to maintain the symmetry. Now you will say all these points should be at same potential, yes. So they can be joined, yes. Once you join this point here, what you get is a circuit of R, 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 one more R by 2, and here also R by 2, R, R, and one more R. These are joined. And you can say that the resistance of left half has to be same as the resistance of right half. So I just need to find the resistance between A and this point C and double it, right? Because both are in series. So you will say here you have got R by 2 and R in parallel. Their equivalent resistance will be R by 2 into R upon R by 2 plus R, that is 3R by 2. So here you get R by 3. So the resistance of this much part is R by 3. This R by 3 is in series with R. So R by 3 plus R, the resistance of this whole upper part comes out to be 4R by 3, R by 3 plus R, 4R by 3. And this 4R by 3 whole upper part is in parallel with R. So what you get is 4R by 3 into R upon 4R by 3 plus R, that becomes 4R by 3 into R upon 7R by 3. Cancel out bacho, R by 3, R by 3. So what you get is 4R by 7. So if the resistance of this half is 4R by 7, other half will also be 4R by 7. So what you get, the answer is as 8R by 7. So this is one of the method to solve this question. Now I will teach you other method. You can break this part of the circuit. Here you have got join, break this join and think that the circuit looks like this. So how can you do this? We'll explain, 1 second, wait for it. You can say that this is what the circuit actually is. There is no joint here. Sir, how can you break it? Reason being, you will say that because of the symmetry, the current entering, if here is I1 and here is I2, then the current exiting from here has to be I1 and here has to be I2. If the current in this whole lower line remains same everywhere to be I2, it means that there is no current entering and exiting effectively from this upper part. So whatever current comes from this upper part, that gets diverted to the upper part. If the current coming from upper part gets diverted to the upper part, we can think as if there is no point of connection here. We can break this connection. And once we have broken this connection, game over. You will say that these two resistances R and R are in series. So you get effective of 2R. This 2R is in parallel with R. And then you have got this R drawn here and here. And there are two more resistances drawn here. So here I have used two methods. First, I have joined this central point dividing this upper resistance R into two resistances of R by 2, R by 2. Or you can use reverse symmetry and say if current entering from here is I1, I2, then the current exiting also have to be I1, I2. And there is no current exchange here at this junction. Since there is no current exchange, you can break this part of the circuit. So here you will get these two R and R in series. They give you 2R. Okay. 2R parallel R gives you 2R into R upon 3R, that is 2R by 3. So think over it. So now you have got this 2R and R in parallel, these R and R in series, and this R to R parallel combination, and this R to be the upper line series. So replacing these two, you can place only one 2R, and replacing these two, you can place only single one 2R by 3. Now you have got this R, this 2R by 3 and this R in series. So the equivalent resistance of the upper line comes out to be R plus 2R by 3 plus R. That comes out to be, take the common denominator 3. So that will give you 8 R by 3. So that will be the resistance of upper line. Now once you know that resistance of upper line is 8R by 3 and lower line is 2R, take their parallel combination. So you get R equivalent to be 8R by 3 parallel 2R, that will give you 8R by 3 into 2R upon 8R by 3 plus 2R. So that gives you 8R by 7 as your final answer. Let's move on to the next example. In the figure, current is 0.25 ampere. Then find the value of R. So there is this circuit and they have said that in this particular figure the current is 0.25 ampere. What is the value of R? And these type of questions are very basic questions. So if you know the EMF of the driving cell and you know what is the main current, you know what is the effective resistance of the circuit. So from delta V equals to IR, you will say that 12 equals to 0.25 into R, or R comes out to be 12 upon 0.25, which is as good as 12 into 4, so that gives you 48 ohm. So the equivalent resistance of this whole circuit has to be 48 ohm. Now how to solve? Very simple. You will say these 60, 20 and 10 are in parallel and the parallel combination of this 60, 20, 10 is in series with R and the effective resistance of this whole line is 48. So you will say as I equals to 0.25 and potential equals to 12 volt, this means that the R equivalent of the circuit has to be V by I, that will be 12 upon 0.25, that has to be 48 ohm. So the equivalent resistance of this whole part has to be 48. Now from the circuit we can say that R equivalent has to be equals to R plus the parallel combination of 60, 20 and 10. What is the R equivalent for parallel combination of 60, 20 and 10? So you will say 1 upon R equivalent as they are in parallel equals to 1 by 60 plus 1 by 20 plus 1 by 10. Now beta, take the common denominator as 60. So you get 1 plus 3 plus 6. So that becomes 10 by 60. So 1 upon R equivalent equals to 10 by 60. Flip both the side. So you get R equivalent equals to 60 by 10, which is 6. So the parallel combination of 60, 20 and 10 gives you an equivalent resistance of 6. So you can say that R plus 6 has to be equals to 48. If R plus 6 has to be equals to 48, this means that R has to be 48 minus 6. So R has to be equals to 42. Simple question. Now I'm going to end this R with the important question which many of you have got problem in, which is the ladder series question. Now all the ladder series questions are easy. All you need to do is answer this simple question. If I ask you this question which you have seen in your class 8th or 9th, that kids, if x equals to 1 by 2 plus 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 1 by 2 and so on, then what is x? Now the way to solve this infinite question which has been taught to you in your earlier classes is that if you hide this upper part and start looking from here, it's the same thing. So if this whole thing is x, then starting from here till the end, it is also x. So you can write from here x equals to 1 by 2 plus x. And then you can solve this particular equation to find the value of x. So you will get 2x plus x square equals to 1, or x square plus 2x minus 1 equals to 0. From the solution of quadratic that x equals to minus b plus minus under root of b square minus 4ac upon 2a, I can find out what is the solution, and that will be the value of x. Tomorrow, if I give you question like x equals to under root of 3 plus 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 under root of 3 till eternity, what is the answer? The same procedure is used to solve. You will say if this whole thing going up to infinity is x, then this whole thing going up to infinity also have to be x. So you will say that x equals to under root of 3 plus x. Squaring both the side, you will get that x square equals to 3 plus x, or you can write x square minus x minus 3 equals to 0. Now using the solution of quadratic that x equals to minus b plus minus under root of b square minus 4ac upon 2a, you can get the answer. So sir, you are saying that infinite ladder series questions are like that only? Yes. The question goes something like this. The equivalent resistance between point A and B of an infinite network of resistance, each of 1 ohm connectors as shown is. So your mission is to find the equivalent resistance between the point A and B. And here you have got an infinite ladder of each of resistance 1 ohm. So how to solve? So you will say, if I forget this much part and start focusing between these 2 points, doesn't it look the same? If I hide out this much part and say the circuit starts from here, let's call these points C and D. So going from C and D to infinity is as good as going from A and B to infinity. So if the equivalent resistance between point A and B have to be equal to R, then the equivalent resistance between point C and D also have to be equal to R. So how to solve these type of questions? So suppose the effective resistance between A and B is R equivalent. Since the network consists of infinite cells, infinite units, if we exclude one cell, the first part, from the chain, remaining network have infinite cells. Cells means units. Cell, the building block of life, right? So cell means units, not the battery here. Okay, so the remaining network have infinite units. Effective resistance between C and D will also be R equivalent. So if you think of point C and D and remove the first part, the effective resistance between C and D will also be equal to R equivalent. So you can think of the circuit. So if the equivalent resistance between A and B comes out to be R equivalent, then the equivalent resistance between C and D will also be R equivalent. Now place one resistance of R equivalent and write down the equation. You will say the equivalent resistance of this whole circuit between point A and B will be R is in parallel with R equivalent, and this R and R equivalent parallel combination is in series with R. So you will write the equation as R equivalent, the equivalent between A and B, forget this part once, equals to R plus the parallel combination of R and R equivalent. So if you write down the parallel combination of R and R equivalent, what will you get? R into R equivalent upon R plus R equivalent. So here you will get R equivalent equals to R plus R into R equivalent upon R plus R equivalent. Now sir, how to solve this? The same way you solve any goddammit quadratic equation. So here you will multiply this R plus R equivalent to each term, and then you will solve for R equivalent using the quadratic equation. So on solving, your R equivalent comes out to be 1 by 2 times 1 plus root 5. I recommend you to go up to the answer for this question and check the result. That's all in this hour. See you guys in next hour, where we will talk about devices like voltmeter, ammeter, how to make voltmeter and ammeter out of galvanometer. Then we will talk about meter bridge, and in the end about potentiometer. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.